Okay, so yesterday, at the end of the day, you were asked to, there was 5 little stories, right? 5 little stories, position time graphs. If you weren't here yesterday, then you need to get that. They are up here. Anyone not here yesterday? Okay, and the first one says a ball is thrown in the air, it lands on the ground at your feet. That's the one you have? Okay. A ball is thrown up in the air, it lands on the ground at your feet. 10 seconds later, position is measured in the vertical plane. In other words, we're measuring the height of the ball. So what does the graph look like? A hill? A round hill? Okay. Now, you're throwing it from like shoulder height, right? So what would be the initial position? What height? Approximately. Maybe 1.5 meters, right? You throw it up, and then it lands on the ground 10 seconds later, right? So is it going to be a hill like this, Connor? No? Why not? Yeah, so it's got to actually start up here and then go like that. And because it lands 10 seconds later, you should probably label the time at 10 seconds.
That's a
tall person? Why is that a tall person?
Because no one has an arm all the way up there.
That could be one. That could be like 1.5 meters.
Exactly.
And then to make a ball like stay in the air 10 seconds, you gotta have a really
Throw
good throw.
You're right. So it would probably be more. Maybe what Sonia's saying is that to make it a little bit more accurate, maybe it should be more like about like this. Maybe 1.5 should be there.
Yeah, like that.
Okay.
Yeah. I think
That's what you're saying. Okay. I'll go along with that. I'll go along with that. That's okay. Yeah. Okay, now number 2 says, what if the position was measured in the above example in the horizontal plane? In other words, we didn't care about the height. What we cared about was how far left or right it went. What would it look like? Now this one is hard, because now we're not talking about the height, we're just talking about how far away from me it is. It would stay the same, right? Now, it depends. Are you counting the distance from my hand? Because then the distance would be this way. It would be 0. If you're counting it from my shoulder, then it would be, I don't know, maybe 80 centimeters, right? So it would either be 0 if you're using my hand as the frame of reference, or if you're using sort of my shoulder as the frame of reference, then it would be something like this, right? But it would always be the same value. How come? Because we're not measuring the height, Larissa, we're measuring the what? No, we're measuring the distance away from me, right? If I throw the ball up in the air or the roll of tape or whatever it is, how far away from me is it? Guess. 80 centimeters, right? When I throw it up in the air. Does it ever become more than 80 centimeters?
K and L. Please make your way down to the motion for pictures. Thank you.
Is it ever more than 80 centimeters away from me? This way?
Yeah.
What? But it isn't. It goes straight up.
How do you know how do you know it's asking that though? I don't understand.
The question says, what if the position was measured in the above example in the horizontal plane? What's horizontal? Left to right. Not the height.
Yeah, but when you put time on the vertical axis?
No. Time is down here. So this is time, and this is distance, but horizontal distance. How far away from me? This way. What I'm trying to show you is that it's not always the vertical height that we can measure. It could be something else, right? It could be horizontal distance. It's a little confusing. It's not a big deal. Not a big deal. All right, let's try number 3. A man walks for 8 minutes from his home on Main Street north to the Royal Bank. Now, the Royal Bank is downtown, right? He's walking from Main Street north, like up by, the courthouse kind of thing, right? He spends 2 minutes at the ATM and then returns home. Now, there's a few things you have to think about here. Number 1 being, what is his frame of reference? In fact, there's more than one answer, I would say. What are you going to use for your frame of reference? Home or the Royal Bank? Either one. Let's do his home first. His home is at 0. Okay, he lives the north end of Main Street, right across the street from the courthouse. It's an H for home. He's walking south to the Royal Bank. Which direction is that, positive or negative?
Negative.
South is negative.
That's not safe.
It doesn't, but it says he lives at Main Street North in the Royal Bank. Where's the Royal Bank? You live in Dauphin, don't you? Think. Well, too bad, Sonia. Physics is about thinking. By the time you are finished with me, you will have learned to think.
But his house could be on the other side. and
Could be,
he
but that's
on-
Main Street South.
True.
But that's okay, Mr. Swanner.
He keeps walking
So if you want to-
No, but you're thinking. See, he knows. He knows where Main Street is and the Royal Bank kind of like. All right, so I'm
Off to a little spot. How am I supposed to
Yeah,
know
what
which
if he
one's which?
keeps walking north to the Royal Bank? We don't know that.
Where he just said he's. I'm just,
What if
no,
there's food and I don't know about it? That's okay.
right. So you would ask.
yeah.
I'm clarifying it for you now.
For years. How do you?
She's good. Anyways, we're at Main Street North. Maybe I'll put a map in the question for future reference.
Yeah, you should.
All right, maybe I'll do that. I'll put a little Google map in it for you. So we're walking from the north end of Main Street. We're walking south to the Royal Bank. We're walking negatively. Most people, when they walk at a
Steady.
fairly steady pace. So I'm going to show that by a straight line, and it's going to be negative, right? So I'm going to be walking along my straight line, blah, blah, blah. I stop at the ATM for 2 minutes. What's my displacement during that time? Nothing. I'm basically stopped, right? And then he returns home, which is his position 0. Now, if you include the bank, if I start my bank as my frame of reference, then what does it look like? I'm starting in a positive position, so I start way up there, right? Am I still walking south? Yes. Is my slope the same?
Yeah.
Yeah, except when I get to the bank, now I'm at position 0, and then I go back home. So both of those are fine. Depends on your frame of reference a little bit here. You'll notice that the shape is exactly the same. It's just moved up or down. Okay? You don't have to get it 100% yet. I'm building towards knowledge. Okay? Don't worry. What about a bowling ball? Spending 8 minutes in the rack waiting to be thrown. It takes 4 seconds for the ball to reach the pins and then 20 seconds to return to the rack. Is this not almost exactly the same question? So once again, we're left with the decision, is the rack the 0 or the pins the 0? Because it matters, doesn't it? Right?
It's not calculate how much time it takes first to line up.
That's true, right? And do the little Fred Flintstone thing.
Yeah, exactly.
Okay, so if the rack is 0, okay, so I'm standing there, there's the rack of balls, I pick up a ball, right? What's the ball at? What position?
Here.
Relative to the rack? 0, right? And I throw the ball, right? And it's moving. Now, is moving towards the pins positive or is moving towards the pins negative? Is there any north-south in the question? No. So what would you, kind of an assumption would you make? Positive, right? If in doubt, assume positive. Okay, so the rack is at 0. Does the bowling ball travel at a constant speed? Does it speed up? Does it slow down? Fairly constant, right? There's a little bit of speeding up when you throw it. Tiny bit of slowing down, but not really, right? So it's going to move more or less at a constant speed, and it's going to hit the pins, and then it's going to do what? Sort of bounce around down there for a second or two, right? And then, now it, actually,
Okay, what about the 8 minutes?
what about the 8 minutes? I just realized that. What about the 8 minutes? I know, so I'm going to go back.
Stays there at the 8-minute point.
Okay, is that what you want to do, Connor? So what you're saying is, Connor, is that I want to move this whole thing over there, and I should label that 8 minutes. In fact, 8 minutes is pretty big. I'm probably going to have like one of those little break thingies, and remember, did you taught that in junior high? Little break, like, really? Oh, I did tell you that, didn't I? Oh, well, this is an exception. It only matters when you're doing like data from like an experiment. Yeah, no, we're talking about the shaker. Okay, so 8 minutes. is the shape still good though? Shape is still good, and then it takes 4 seconds for the ball. 4 seconds for the ball to reach the pins, and then 20 seconds to return to the rack. So that's 8 minutes to there. Is that going to be 4 seconds? I don't think so. It's going to have to be what? Like almost straight up and down, right? And then it bounces down there for a second or two, and then it takes 20 seconds to return. So it's a little bit more like that, isn't it? Right? Right? The first one is steeper. How come the first one is steeper? It takes less time, and then the next one is a little bit flatter because it's taking a little bit longer. It's okay if you don't get this 100%.
I definitely did.
Okay. It's all right. Okay. Well, maybe number 5 will be better.
It's not.
And if I guess I should do it. Now, what if the pins are my 0? Does the shape remain the same? But what do I have to do with it? I have to move it either up or down, don't I? Right? So, where do I put it? If the pins are at 0, then that means, are we going to say the rack of balls is in the negative territory or positive territory? Negative, because we've already established that towards the pins is positive. So in other words, what it would look like, would it be up here?
No.
It would be? In fact, do I know exactly how far down to go? Right to there, right? How do I know not quite to there. How do I know to go there? Because when the ball gets to the end, the pins, then it's 0. So that would be my 0. Now I probably should have, on my graph, this line here. What does that line show?
8 minutes.
The 8 minutes that it's just at rest. Exactly.
On a test, do you even tell us what our favorite reference is?
Probably, yeah. Yeah. You guys worry too much about the test. I understand. Girl leaves her locker by the office. Now, this would be the DRCSS office.
You didn't specify.
You did not.
Yeah, I know. I'm
I
specifying
looked
now.
once.
Bunch of wannabe lawyers in the room. A girl leaves her locker by the office and starts to walk to the gym. That would be the DRCSS gym. Not another gym. She walks 15 meters in the standard metric system. Not like the Klingon system of some kind or something like that. Yeah, so I don't know, or whatever, right? Before realizing that she forgot her gym clothes, she returns to her locker, gets the clothes, and then proceeds to the gym, the same gym that she was walking to before. All right, so what's it going to look like? Now, most of the time, people are going to assume that the origin is where you start. So let's just say, okay, the locker is where she starts, right? If in doubt, Larissa, on the test, you would just use the starting position as your 0. Okay, so she's starting in her locker, she's walking towards the gym. Is that positive or is that negative? Well, we know here at the DRCSS that direction would actually be south, so I would certainly accept negative, but positive probably okay, right? She's walking forward.
Who really calculates?
Yeah, no one does that. We'll assume that she's walking forward. Okay, so she's walking to the gym at a reasonably constant pace, realizes that she forgot her gym clothes, so what does she do? She turns around, right? Slows down, turns around, and goes back. Then she stops in her locker. That's going to take a few seconds, right? And now she has to run to get back to class.
No.
Well, yeah, she's going to be late. Maybe she left early. No, it's not going to make a difference? Okay. So, is there anything different here now? Like, just like that?
Yeah, so far goes up.
How come higher, Connor?
Because then she goes all the way.
Yeah, she goes all the way to the gym. We don't know how far the gym is, but something like that, right? Something like that. Did you sort of kind of have that?
Yeah.
All right. Okay, well, let's go to the back side here. Mr. Bennett's playing with the crash carts again. So you saw that yesterday, right? He has a motion sensor hooked up to it, and the following position time graph is recorded. What is happening in the first 2 seconds? Moving
That way.
to the right. Moving forward to the right. How many meters has the cart traveled at point A? Well, I went 2 forward, 1 back, that's now a distance of 3. 2 forward and 1 back. I've traveled 3 altogether. And then I went from 1 to 5, that's another 4, so I've traveled a total distance of 7. I've traveled a total distance of 7. I've traveled a total distance of 7. Now, how far is the cart from the stating point? How far is the cart from the starting point when he's at point A? I'm at plus 5. Which one of those two numbers, the 7 or the 5, is the distance traveled? 7. Which one of them is the displacement? The 5. Notice the difference, please. What's happening from A to B? Stopped for 2 seconds. How many meters does the cart go altogether? Am I asking for distance or am I asking for displacement? Distance. So we've got 7 to A, then I'm going 5 all the way back to minus 3. That's a distance of 8. So now I've got 7 plus 8 is 15. And then I go one more back, a total distance of 16 meters. Is that a vector or a scalar quantity? That's 16 meters. Sorry, the distance of 16 meters. Is that a scalar or a vector? Why is it a scalar? It doesn't have a direction. I didn't care about whether I was going forward or backward. I went a total distance of 16 meters. Now, how far is the cart from the starting point when it gets to the end of the trip at point C? Minus 2. So my total distance is 16, and my displacement is minus 2. And of course, this one is the vector. Okay? Please note the difference. All right, the last one here. A student leaves the door of the physics classroom. That's the origin. She walks down the hall, stops for 3 seconds, then back to class. Did I miss one? Oh, did I? Oh, I must have the old version. Okay. Oh, what is the cart's average speed? What is the cart's average velocity? Oh. Okay, well, that's what we're going to talk a little bit about today. So what is the average speed? The average speed is the distance, 16 divided by, what's the time? 8. So the average speed is 2. The average velocity is the displacement, minus 2 over 8, or minus 0.25. Okay?
There's no direction. Well, I guess you could say, but you would say
Is
what?
that an 8?
The negative. Yeah, the negative, right? So the velocity is minus 2 divided by minus 8, right? Minus 0.25. So here, yeah, oddly enough, her overall speed is, well now, I was going to say overall speed is positive, but isn't the speed always going to be positive? And I use the finger quote thingy. Because is it really positive? Or it just really doesn't have a sign? Doesn't really have a sign. It's just 2, right?
Where did the 8 come from?
Just 2. What's the total time, Larissa?
Oh.
Okay, good question. The 8 comes from the time. Good. Okay, now can I go on? I'm good? Okay. Thank you. A student leaves the doorway of the physics class in the origin. She walks down the hall, stops for 3 seconds, and then walks back to the class. The total distance traveled is 20 meters, and the total time of the trip is 11 seconds. Make a position time graph to illustrate this motion. Well, what's the first thing that you did? You drew the lines. How did you know where to draw them, Alex? Can you be a little more specific? Well, if I was doing this, I would say to myself, well, if the total time is 11 seconds, and I have to end up exactly where I started, right here at 11, I'm going to do that, because that's where I got to end up, right? And where do I start? There. Okay. He stops for 3 seconds. So there's a stoppage in there somewhere. That's going to be a flat line, right? How much time is spent walking? 6. 8, right? 11 minus 3, 8 seconds. Now, the lawyers in the room might say, well, you don't know that she walks forward at the same same rate that she walked backward. But for the most part, I think we can assume that she's going to walk there just as fast as she's coming back.
going to work slower.
She's probably slower back because she doesn't, not so keen to come back, exactly. But if we went with the same speed, then I guess if she's walking for a total of 8 seconds, then that would be 4 there and 4 back. Now how far does she go if she goes a total distance of 20?
10 meters there, 10 meters.
That has to be the same, right? 10 and 10. Okay, so what I'm getting at is at 4 seconds, she goes all the way to 10. Then she stops for 3, and then returns. Does that make sense?
What happened in the middle? Where is the white?
Oh, just my pen, yeah. She just didn't exist for a second there. Yeah. She slipped in a portable hole or something, I don't know. Fell out of existence. Yeah.
Teleported.
All righty. Okay, well, we sort of introduced a few things there.